Let's talk about now transforming our parent function f of x equals a to the x. Well, hopefully it's second nature to you by now. If I had f of x equals a to the x and I wanted to find g of x equals a to the x minus 3, that would be our graph, crazy, cuckoo, bizarro, bonkers, translated 3 units to the right. How about h of x equals a to the x outside of this parentheses plus 2? Outside affects the y. We'd be raising this by 2, including our horizontal asymptote. Whoa, look at both of these together. This would be the parent function moved 3 units to the right and up 2, including its horizontal asymptote. And now we'd have to consider all of these transformations. This would be to the right, this would be up 2, this would be reflect over the y-axis, and this would be reflect over the x-axis. We're going to do examples with all of those. If I ask you to graph g of x equals 3 to the x plus 1. Now, this is the exponent. I can put it in parentheses if I want to. The parent function, note, is 3 to the x. So if I'm asking for g of x equals 3 to the x, this is the equivalent of f of x plus 1. Wherever I saw x, I now put x plus 1, and it gives me this function. I mention that because when I give this to students, they have no problem graphing it. But when I say this, most students freeze and they don't know what I'm talking about. I'm just saying wherever you see an x, now put an x plus 1, which would give me this g of x function. Now, in order to do that, I might graph the parent function. I know very quickly that I have exponential growth because my base a is greater than 1 and my exponent is positive. So that goes through 0, 1 and 1, 3. I have this horizontal asymptote at y equals 0. I have to know that this is going to move, this is crazy, cuckoo, bizarro, bonkers, it's going to move me 1 to the left. So 1, 3 is now going to become 0, 3. And 0, 1, if I move it to the left, is going to become negative 1, 1. So my final graph for this function, g of x, is going to look something like that. Here is g of x. It goes through negative 1, 1, and 1, 3. I'm sorry, 0, 3. Those are the 2 points it goes through. Notice it still has a horizontal asymptote at y equals 0. When you graph this g of x, I want at least 2 points and 1 asymptote. 1 asymptote, 2 points, and I draw the shape of it. I've done my job. Again, for the parent function 3 to the x, I'm asked to graph a transformed function, h of x equals 3x minus 2. Now, when I give this to students, they have no problem. If I say to them, graph f of x minus 2, most freeze. These two mean the same thing. I can substitute in for f of x 3 to the x minus 2. They're the equivalent. So h of x, well, I might again start by graphing my parent function. I know my parent function looks like this, and it goes through the point 0, 1 and 1, 3. This is f of x equals 3 to the x. Now I know that this transformation, negative 2 on the outside, my parentheses here just include my exponent. So this is going to say move everything down 2. So this move down 2 is going to be here. And that new point is going to be 0, negative 1. I moved the y coordinates down by 2. 1, 3 is going to become 1, 1 when I move it down 2. And here is the critical piece here. Our horizontal asymptote was at y equals 0. Now my horizontal asymptote is going to be moved down 2. And I've got this, y equals negative 2. So to graph this child function of the parent function, I need at least 2 points and 1 asymptote. And I can still show exponential growth because my base is greater than 1 and my exponent is positive. So I've done my job. 2 points and 1 asymptote. I've drawn it and I've labeled each of the 3 components that I'm looking for. For the parent function y equals 3 to the x, I know that's exponential growth, I'm asked to graph the child function k of x equals negative 3 to the x. Now, here is my x, and I know inside, my rule is inside affects the x, and it's the crazy cuckoo bizarro bonkers world. Everything that I think is going to happen actually goes opposite. A negative moves me to the right, a positive moves me to the left, etc. Now here, outside affects the y. I'm going to take the opposite of the y values. So I know this is going to be reflection over the x-axis. Again, to draw my child function, I start out with my parent function, exponential growth, through these magical points, 1, 3, and 0, 1, and we've got this beautiful horizontal asymptote here at y equals 0. Now, what this says is take the opposite of the y values. Well, here is my y value, 1. It's going to give me 0, negative 1 if I take the opposite of the y value. Here is my y value, 3. If I take the opposite of that, I'm going to have this point, 1, negative 3. And I can see, I'll draw it dotted here, I can see that I've got this kind of shape. Notice the y equals 0, that's the x-axis, remains my horizontal asymptote. Nothing changed in that regard. This negative on the outside, remember, that affects the y values. So the y values will change. Positive y values become negative. Positive y value becomes negative. We're reflecting over this horizontal axis here. And this is our graph. Notice 2 points and 1 asymptote. I've done my job. I've graphed it. If the parent function is f of x equals 3 to the x, and I'm asked to graph j of x equals 3 to the negative x, well, we've already done this, haven't we? First, graph the parent function. We know that's going to go through 0, 1 and 1, 3 and have this horizontal asymptote at y equals 0. Now, inside this parentheses affects the x. So I'm going to take the opposite of the x. 1, 3 becomes negative 1, 3. And 0, 1 stays 0, 1. So our graph here that I'm doing dotted here will be this exponential decay. But we already knew this, that this would be the same of 1/3 to the x for reasons we talked about in another video, which of course puts our base positive, but between 0 and 1, so that's exponential decay. Or you could think of it as this, which means it's a reflection over this y-axis. They're mirror images of each other. Look, I've got 2 points and 1 asymptote. I've done my job.